How's it going, everybody? ZoinkMeister Patrick here, joined today by ZoinkMeister Adam.
Hello. I haven't finished this book I started reading. It's The God Theory by Michio Kaku.
I think I've seen that at your place.
Yeah. It's basically a book. Michio Kaku is a very famous American-Japanese physicist.
Okay.
And basically the book goes over some proponents for string theory and explaining it in a way that, maybe you're not a quantum physicist, right?
Right, yeah.
But also, the first two chapters basically give you the starting foundation for classical physics leading into quantum. And it's been probably the best summary I've ever read of okay, so you don't understand things. Here's a really good jumping point. Everything from Newton to Einstein and everywhere in between.
Yeah.
Works of Maxwell, Edison's discovery,
That's cool.
Tesla's, all that stuff. It covers all of it. It's really good. I like it. Cost me $15.
I'm taking a graduate level quantum course right now about nuclear magnetic resonance.
Yes,
machines.
I remember you.
Yeah, and it is so much. Oh man, I hate quantum stuff. It is just equation.
I love quantum stuff, but I'm not doing equations on it. That's all. Have fun.
Equations worth 1,000 pictures worth 1,000 words. Equations worth 1,000 pictures.
Oh man.
Oh, it's so bad. It's just calculus. It's just multidimensional calculus. It's a lot of multidimensional calculus.
You didn't have enough of that, honestly.
And differential equations.
You didn't have enough multi-dimensional calculus.
And electron, magnetic, physical theories. And it's a lot of actually surprisingly how our waveforms are captured. Turns out NMR machines, this is way too nerdy for at this point. If you're sticking around, I'm sorry.
This is surpassed nerd. This is straight. We're talking.
Yeah, we're talking limits of understanding of the universe here. But okay, so basically NMR machines, I'm not going to get too much into the technicals of it. There's not a point.
No, go ahead.
Point is that the
Make
file...
this a separate episode inside.
The file that comes out, the output of your NMR machine is in radio frequency waves. So it's radio waves. But radio waves are really high energy. So storing those data points, what the heck was that? You missed it.
I missed it. What
was
was
it?
It
was so creepy. There's just a dude, with a clown face, just appeared on the screen, in the background. It was crazy.
I took my headphones off, put them on my head, and then turned to look at Patrick.
I've never seen that before.
Oh man.
Okay.
I'm gonna have to watch that in post.
Yeah. Okay. So anyway, sorry. So it comes out as a radio frequency wave, but that's a lot of data points, and you lose a lot of precision if you try to store. I mean, back in the old days, nowadays there's plenty of data, but they cut off the first. So radio frequency waves are somewhere in the megahertz range, so about 4 million hertz or whatever. So what they do is they just cut off that 4 million. Because the actual difference between the reference wave, which is at 4 million, and the output wave is 2,000 hertz, which is in the audible range. If you, for people who don't know, the audible range is about 30 hertz to about 20,000-ish hertz. So all they do is they chop off that end data point, that 40 million. You just save the 2,000. So your output on an NMR is actually an audio file. Not in that it loves music, but in that it is a PI
audio-based file.
Yeah, not audio file like PH, audio file like FILE. Anyway, you can actually hook up a speaker to your NMR and it'll play music. There's a paper written in Journal of Chemistry Education where somebody made music using an NMR just because it was audio files. So you can just hook that up to speakers and actually hear the NMR, and you could even tune the NMR by listening to it and stuff like that. It's crazy.
You do an
NMR?
Sorry, MRI, and it's it's just the House of Holden. Starts
There, that guy.
The bird?
No,
that creepy guy at the top of the screen. Okay.
That's what I saw.
Yeah, future Patrick's gonna have to do an arrow or a virtual zoom or something.
Probably, yeah.
I thought it was a whole face. On
no.
Right.
Yeah, it was just
how did I miss that?
Popped out in the corner there.
Yeah, that's that is quite the thing. I recently heard, I'm not sure if it is true, so you're gonna have to do some of that background Jesus pants research, like I said.
This big boy.
Yeah, you have to do some.
What is it?
Go Google it. Basically,
you know what I like.
Apparently tigers make a sound.
Okay.
That is very, very scary.
Okay.
That is below our audible range.
Oh, okay.
So other animals that can pick up that range.
Yeah.
Apparently it's really low and really terrifying.
Yeah.
And they're just stuck in fear.
Yeah.
Whereas we are just unable to hear it. So we're just
great.
and?
I will for sure look that up if I catch it in post.
Yeah. I mean,
that sounds interesting.
Yeah, it's not something like inhumanly impossible, right? There's shrimp that for some reason have 16 million extra color sensors.
Yeah.
It's why? What does that shrimp need to see down there?
Yeah,
right?
we have 3, and then they have
16.
16.
16 million more combinations or some nonsense like that. It's like, man, don't you live at the bottom of the ocean? But maybe they see rainbow right at the bottom of it. We don't know. We're not a shrimp.
There was something. Oh yeah, so yeah, if you want to ever listen to a molecule, you could actually listen to, that's kind of what the NMR sound output would be. Because the output is you do a Fourier transform to get it to display the different frequencies of the Lamar precession as it comes to equilibrium. And so you basically are like listening to the molecules spinning. It's called nuclear magnetic resonance because it's the nucleus of the atom spinning. That's the nuclear part. So yeah, you can actually listen to molecules spin, which is crazy to think.
I don't know if you've seen.
It's like recently, a whale stuff where it's like.
The sound of a black hole was released.
Oh really?
Yeah. I guess you need something for waves to bounce off of, right?
Wait.
So you can record sound. And space has a whole lot of gas in it.
Okay.
So apparently they were able to do some fun thingamajigs where they were able to basically recreate the sound that would be emitted from a black hole.
I feel like if it were in an atmosphere, I guess because I feel like if it's in the middle of space, I feel like you wouldn't hear much.
Probably not. I mean,
like that feels like what's the sound of a starship blowing up in Star Wars? It's like, well, I mean, it should probably be silent.
I mean, you could probably definitely feel a wave of some sort, right?
Right.
But and then
how could you? There's no mass transfer.
I mean, there might be, right? What if there's like a I really don't know. Who knows? We haven't blown up in space,
right?
But at the same time, we could look up the exact
sound
I know I'm
of
not
a black hole.
Oh, I know what the sound is. It sounds really eerie. I could see how they did it.
It's just like very clearly the like 2001: A Space Odyssey.
Not even that. Yeah, it's like 1940s. Let me see.
Boom, 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 boom.
NASA's audio of a black hole has gone viral. Here's how they created it. To create an audio that is audible to humans, scientists do something known as sonification, which is the translation of this astronomical data into sound. Hold on, this seems like a very broad.
Sounds like they just made it up.
While I search this up, future Patrick, if you could just put the sound on screen for a little bit. Okay, the idea that there's no sound in space is a popular misconception. Most of space is a vacuum that sound waves can't move through, but galaxy clusters can release a lot of gas, which envelops the many galaxies inside of them, creating a medium for sound waves to travel through. In 2003, astronomers found that the pressure waves sent out by a black hole at the center of the Perseus galaxy cluster caused ripples in the cluster's hot gas, which could be translated into a note. The thing is, the note is too low to be heard by humans because it is 57 octaves below the middle C, according to NASA.
That's a lot.
Yeah, it's really far. 57 octaves.
Yeah.
To create audio that is audible to humans, scientists do something known as sonification, which is the translation of astronomical data into sound.
Okay.
NASA says the sonification of the Perseus galaxy cluster is unlike any other done before because it uses actual sound waves discovered by its Chandra X-ray Observatory Space Telescope.
Oh, wow. Okay.
Here's the gist of how the sonification was put together. The sound waves were extracted outwards from the center of the cluster. The signals were resynthesized into the range of human hearing by scaling them up 57 and 58 octaves to their actual pitch. The radar-like scanner on the image allows us to hear waves emitted in different directions. The scaling up of the sound signals means that we're hearing is actually 144 quadrillion and 288 quadrillion times higher than the signal's original frequencies.
Okay, I'm not gonna lie. If something is 57 octaves below middle C, it is probably like fractions of a hertz. Like, yeah, like I think like 8 octaves below is like that like 30 hertz range or whatever. So like if you're like, that's basically not making noise. Like sure, it's causing waves of sound, but yeah, I mean, that's like, it's hard to call that like, yeah, sure. If I could listen to freaking like, you know, radio frequencies or like gamma frequencies, like, yeah, I wouldn't be able to hear anything.
That's sharp.
Yeah, exactly.
Ooh.
Like, yeah, so
there's some sharp waves right there.
That is an interesting choice. Hey, this is ZoinkMeister Patrick from the Editing Future. I'd like to weigh in on a couple of the things we talked about at this moment, just to clarify some stuff that I didn't understand when I originally was hearing all this from Adam, just because I hadn't actually looked at it myself yet. So, a couple things. First of all, I want to address what I just said about hearing gamma rays or something like that. Gamma rays and X-rays and radio waves are all within the electromagnetic spectrum, so it'd actually be more accurate for us to be able to see those if we had expanded visual capabilities. You'd never be able to hear a gamma ray no matter how good your ears are. That's just not how that works. I don't know. I was listening to that back and I was like, I don't know what I was saying there. It's just random. The other thing to note is that the sound of the black hole, with big ol' air quotes on my end here, is actually, it's a sonification of the visual data they received from the telescope. So they didn't have like a microphone strapped to a satellite, in case anyone was thinking that's what was going on there. What they did was they took a picture of the galaxy and then they kind of like drew a line out from the center, which you can see now that I've seen the video there. And they found the frequency emitted by the black hole in that direction and then did that radially over time for you to hear those frequencies lined up together like that, and then translated up very, very high pitch so that you can actually hear it. So the sound being made is the sound that the black hole is actually making, kind of, because that's assuming that the sounds of those gases is the same as the sounds in our atmosphere, which I mean, that's just not true necessarily. And then the other thing that's a little confusing is, once again, I mean, those are actual in the audio spectrum though, like that is pressure waves of gas inside that galaxy. You could never hear it from here because between us and them, that galaxy is a vastness of empty space where no sound could travel. So that is saying that if you were in that galaxy, what you might hear, if your ears could hear, 57 octaves below C, is something like what that sound was, but that sound is, of course, made much higher pitch. So that's kind of a translation of what you might hear. So I don't know. It's a little confusing. It's a little interesting because that's not that whole like little differenting sound file there where it like changes pitch over time. That's not what you would hear if you were in the galaxy. You would just hear one single pitch. If you could just like pause that video on a particular moment and just have it play just that frequency, that's what you'd hear in that space, in that line that was drawn. So it's kind of also a weird translation in that you would only ever hear that whole audio file that we heard if you could like travel in a circle around the galaxy at the speed that travel around the black hole in a circle at the speed that radial little purple line shows what's happening there. So yeah, I just wanted to put all that together, not to crush people's dreams about listening to black holes, but it is kind of a transliteration of scientific phenomena through sound for the sake of artistic outreach sort of endeavor, more so than it is an actual, perfect representation of things that are true in space. It does get some things across that I think are cool, like the fact that you can have sound in space, especially if there's a ton of gas in the space like there is in that galaxy cluster. But, it also, I think, just gets people talking about it and that sort of idea, and the fact that, pressure waves come out of a black hole at all is just interesting, I think it's cool. I'm glad Adam shared it with us, but I felt the need to give a little more explanation here. So anyway, back to the recording past. I'll try to throw that on the screen.
I mean, to be fair, if you consider like what they're doing with the James Webb Telescope, right? That sees an infrared and then just translates that back into the color spectrum for us. So that technically is beyond our visual prowess,
right.
But then translated back in allows us to see farther than we could.
Right.
So, I mean, under that same premise, you could say that, right? It's beyond what we would call sound.
Right.
But then translated to what we would call sound.
Right.
Although vision and audio are very different.
Right.
Still.
But yeah, I mean, no, I do appreciate that, where it's like, sure, if you were to take an infrared spectrum and then shift it up to the visible spectrum so we could see it, then it's like, yeah, this is what it looks like. But it's not what it looks like, because you can look at it and it's not there because we can't see it.
Of course.
But it's like, this is what it would look like.
Yeah, this is what it would look like
if we could see in the infrared. So same thing, I guess. This is what this galaxy would sound like if we could hear 57 octaves below middle C.
Yeah, to be fair, I mean, that edge of the universe where everything's expanding dramatically faster and could be the edge of what we call existence.
Yeah.
Maybe it's just beyond our visual spectrum. And maybe with time, if we develop higher and higher frequency instruments.
See it eventually.
Yeah, what if it's just like clearly a giant face? Like, oh my God.
It's like, what, you thought I wasn't real?
Like, it's just Kill la Kill, like, not Kill la Kill.
Yeah, Promare. Or no,
Gurren Lagann?
Gurren Lagann, yeah. If anyone hasn't seen any of Gurren Lagann.
No spoilers for the end.
It is generally recommended by a lot of people. It's like trigger.
Oh man, I'm not gonna lie. The ending's preposterous. Like, it's completely preposterous.
It's like if you like Evangelion and Kill la Kill and Promare and that one episode of Star Wars Visions where they cut a Death Star in half.
Oh man, that was so good.
That's all Trigger's work. And so this is kind of like trigger before trigger stuff with Gurren Lagann. I think Gurren Lagann actually was the first trigger thing. I think Neon Genesis was trigger before trigger. I don't remember.
Supplemental, if you guys have ever heard of the American animation Megas XLR, that's like,
oh yeah,
that's Evangelion, but with rednecks. Like it's, it's the same.
I need to see that at some point.
It's like the exact same premise. Like literally like monster giant robots come to the planet from like a different time or space or something.
Yeah.
And like,
luckily we hooked up a weird like,
luckily he hooked up his car controller and an Xbox controller, like an original Xbox controller to a giant mech, and it works.
Yeah.
So like he can step on the pedal and also like grab the shifter and like also grab the Xbox controller to make the super robot fight. Yeah, it's so good.
Yeah, that's something else. All right, are you interested in actually playing Hellpie?
Yeah. How long are these 2 episodes clock around? It has to be 2. Like they're very different.
One
is
40 minutes now.
Okay, one is religion versus science, and the other one is like a deep dive into the chemistry world. You should definitely split those 2.
If you want to push this another 10 minutes, then we'd have 2 full episodes.
yeah. We can push this another 10 minutes.
But I don't know where that cut would be. I guess somewhere.
I think right after, because at one point we went to hard, like when you're like, oh yeah, I'm studying chemistry right now.
Oh yeah, that's right.
I think that would be the hard cut.
Yes.
Because one went all science, and the other one was like mostly religion.
I mean, there's plenty. I'm taking the NMR class, so I'm like deep into the world of quantum. If anyone hasn't heard the song, that's Dalton, Thompson, Rutherford and Bohr, Schrodinger and Heisenberg and many, many more. Use their brains to enter in the realm of inner space and found the world of the atom was a weird and wondrous place. That's where I am. I'm inside the atom right now, and I'm making sweet, sweet love.
Oh my god! What the hell? What
trans?
What kind of physics? What kind of chemistry class? Like the professor, like
day 1 of class. Okay, everybody, take off the clothes. It's time to get naked.
What did you say your name was, sir? Oh, it's Dr. Fist. Takes off his robe. There's just like aggressive BDSM stuff underneath. Oh my goodness.
Doctor bigger than you think it is.
Doctor bigger than you think it is.
Oh my goodness, should I throw up? You texted it to me. Should I throw up your Facebook ad?
Oh my gosh, yeah.
We haven't talked about
this
that.
Bad boy. Actually, no, I think I want to save that for the actual Hellpie. Yeah.
Okay. We'll get back to that.
Watch Hellpie, whatever episode this would be. Watch them all just to be safe.
Yeah, 12?
And the demo.
Probably 12. Anyway.
Yeah, we'll definitely save that, because that's like on par for Hellpie, right? Like none of this stuff we have to do has to do with anything with Hellpie.
Right. Like one crazy thing is, here's the thing you probably didn't think. I don't know how much people know about chemistry out there. All right, I understand that it's one of the harder subjects and there's a lot to learn, and you can be real confused with what all the tiny little particles and all their fuzzy little properties. But if you think electron, right, generally considered a negative particle,
yes,
right, a lot of the very, very poor representations of it, of the atom are
is a red circle going around a couple of other blue and white circles.
It's usually the blue circles going around a red big old like clump of red and whites. Yeah. Protons are positive, right? And neutrons are neutral, obviously. Hopefully. I mean, I said obviously there, like somebody's gonna feel like I just offended them.
I'm sorry.
That was not what I meant. I'm sorry.
Well, I just started chemistry yesterday.
Exactly. I didn't realize it was obvious. Anyway, so if you've seen that, like Big Bang Theory's transition scenes where they show the like really bad like boric model, like
very heavily outdated.
Yeah. So if electrons are negative and protons are positive, why don't they run into each other?
Well, because they're in love. I don't. I mean, they're not the same charge. They should stick, right? I don't know.
Right, they're opposite charges, so they should be attracted to one another. Why don't atoms like self-collapse?
Because they probably don't have the charges that people assume they have.
They do. They legitimately have a positive 1 and a negative 1 charge. That is actually real.
Very interesting.
Yeah. So interestingly enough, electrons actually don't exist as particles at all. The reason that we think of them as particles is if you tried to measure an electron, you will collapse the wave function that defines them, and they'll collapse into a single point.
Point of singularity.
Yeah, and so that is the electron as we know it. But they don't actually exist as that single point until you measure it.
That's some Schrodinger nonsense right there.
That is where Schrodinger's equation comes from. That is the point of Schrodinger's equation. It actually defines the wave function that is the electron. So have you ever seen a 2s orbital or a 1s orbital or the 2p orbitals or your d orbitals, your f orbitals?
You're gonna have to throw a lot of these on screen for the people.
Probably.
You're the one name dropping definitions. I was like, I would have kept it broad, but you're making more work for yourself.
Sorry. I'm getting a master's degree in chemistry. Okay, it's not.
Eat your Patrick. Go ahead and put it all on screen.
Go put your middle finger up, turn it back towards yourself. That's how I feel about you right now. All right. So all these orbitals, the way that they look, define that is actually the electron. It's not that the way it's described is this is a probability of locating the electron within the sphere. It's a probability zone, whatever zone of probability. But the electron doesn't exist in that sphere. It is that sphere. It is that shape. It is a wave function. It's an energy function. So it doesn't collapse in. So that's the thing. In the s orbital, it actually has a non-zero, basically location inside of the nucleus. So the electron actually can be inside the nucleus, and your charges will cancel out that way. And actually has a non-zero chance of that happening. So I thought that was really interesting. There's some sort of energy though that repels the nucleus from the electron. So when that happens, it doesn't stay there because I forget what the force is. It's like Coulombic forces or something like that. And you can look up like the energy diagram of like where an electron, it's not important. The point is that's actually how they measure the diameter, or the radius, I should say, of a nucleus, of a proton. Is actually because if you excite an electron from the 2s orbital to the 2p orbital, it goes from existing potentially inside of the nucleus to not being able to exist inside the nucleus. And so they can actually measure that distance that way. And so it's kind of cool. So in case you're ever wondering, how do we know how big a proton is, or an electron is, or whatever, it's that's the method. I know that was probably a little too nerdy.
No, I mean, it's perfectly fine. I mean, in terms of computer, right? Like that's my whole thing, computers.
Yeah.
You don't really run into anything quantum until you get to like basically description of transistors and like electron tunneling and stuff like that.
Yeah.
So like it does come up eventually.
Yeah.
Like at that point, you're doing like hard engineering, right?
Right.
Like,
Yeah.
It's like, are you writing code or are you designing transistors for
Right.
like a chip? Like a very different, all part of the same field, very different parts. I absolutely would never, ever, probably ever, not in a million billion years, no matter how smart I ever became, would know anything about any of this stuff you're talking about because it just doesn't pertain to what I'm doing.
Yeah, it's the interesting thing about computer is that I feel like it's two very different sides to it, right? Where it's like if you're a programming software engineer, it's a very different job from like a electrical hardware design sort of engineer. I feel like you have very different concerns.
Oh, absolutely.
Yeah.
And then, I mean, I couldn't even imagine how difficult that must be when those two worlds do like, not collide as in the sense of like, well, of course the collide's stupid.
Collide,
no, I mean
collide.
like if you're in charge of writing the code for a hadron collider, like that sounds so ridiculously difficult. Like I wouldn't even like, okay, cool. Not only do I have to understand how everything works on a hardware, like a fundamental, and when I say fundamental, I mean like, like to the T microscopic, you know, like, oh man, oof. We gotta write a code that'll like, you press this button and it superheats the plasma to go around the circle and that generates enough energy to power the universe. It's like
the people who are trying to build the suns, the cold fusion
artificial. Oh, did you see there was like a breakthrough?
I mean, I think
they sustained it for like 30 seconds or some ridiculous time like that.
Was it even 30 seconds? I thought it was something like,
no, I don't
it
think
was like more
that
than a
long.
microsecond or something.
No, they've made a stride.
Okay.
I think it was done by the South Koreans too.
Okay, I thought it was just like, it wasn't any longer than like 10.
No, it's recent, very recent. We'll do it by the 2030s. We said 2020s, 10 years ago.
China's artificial sun just broke a record for longest sustained nuclear fusion. In a new world record, China's artificial sun project has sustained a nuclear fusion reaction for more than 17 minutes.
Oh my goodness, that can't be right.
That's January 2022.
The previous record was like only a couple seconds.
Right, that's what,
17 minutes of artificial sun. No,
cost $1 trillion.
Of course it did. Of course it did.
That's crazy. Yeah, for 1,056 seconds. 1,056 seconds. At 700 million degrees Celsius.
I'm surprised they had a facility able to maintain that much heat for that long. That sounds ridiculous. I feel like it's one of those things where like you get a supervillain out of this. Like, not by choice either. It was like the guy who was like the intern who was like by the, get out of there, Jerry. Like, I can't hold it. And then he disappears. But when he reappears, he's like, I'm the flaming skewer or something, you know, like, I'm the skewer boy, or I don't know, something really hot related.
Oh, there's actually a Wikipedia article about the history of fusion.
Cold fusion?
Yeah. So
does it have the most recent breakthrough on there that's like confirmed because you know China?
Yeah. There's more energy yield. Yeah. No, that's it. China's record is 17 minutes 36 seconds. That was in January 2021.
That's outstanding.
Yeah, that's the longest time wise. But the thing is that it takes energy in order to make that work. And so the problem with fusion is they haven't been able to make a system that produces more energy than it takes to actually run the thing.
Yeah.
So that's why you mostly see energy records like that was like 56 megajoules
that
or whatever.
was just literally sustaining, not.
Yeah, it was because like we basically pumped in $1 trillion worth of energy into it, and it didn't collapse. It also didn't produce any energy.
So it was just a waste of $1 trillion.
Yeah, but you know, they got a record. It's China. You know how it is.
Yeah.
So.
I'll have to look it up some other time, or maybe future Patrick can look it up because we're running out of time on this.
Lucky me.
But I want to say it was South Korea that like was able to produce. I think they sustained it for like. It wasn't 30 seconds. It was probably like 10. But I believe the output was slightly more than the input.
Okay.
Which was, you know, the upside.
Right. So that's why, the most recent record is for like the highest energy output that they've gotten from it, because it has to beat the energy input.
What they should do is they should make a facility in space.
In space,
and
man.
then do it up there so they don't need no confinement facility.
Mars, man.
On Mars.
Did you see that?
That way we'll heat up Mars.
We don't have time for this, but did you see that? I think the United States is trying to get back to the moon.
Really?
Yeah, I don't know if you heard about that.
That should be what they have. Okay, look, I'm gonna be honest. Look, Elon, you're crazy, and you made me some money on that Dogecoin, man. You did, you really did. But go to the moon first. Like I know the moon is like you can't blow things up there because of like world packs and whatnot. But that's good. Just establish a moon base before a Mars base. You know how much hurdles you have to go through?
Yeah, so that's the idea. Is they're trying to get back to the moon right now. That's their most recent announcement.
They should absolutely go to the moon. If you're gonna try to go to Mars, accomplish the moon first.
Yeah.
You know how many theoretical problems if you can establish a moon base and have people that are like living there for like more than a year, then I'll feel more confident about a Mars mission.
Right.
But if you're like, no, we're gonna go straight to Mars, we figured it out.
Right.
They're gonna live. Like,
it's way too far to like start there. Like, why start?
Yeah, not even a relay. Like, not even like, there's not even a space station in between those two things.
Yeah.
Like there's not even a relay like in case something goes wrong. When they landed the rover out there was like a 2-minute delay from the broadcast?
Oh yeah. Right.
Oh my goodness.
Yeah.
You know how many things can go wrong in 2 minutes?
2 minutes, yeah.
Like they sent that rover to Mars and then had to wait from the time it broke atmospheric.
Yeah.
They had to find out whether or not it blew up or not. Like you just have to wait. Like it's not.
Are you okay?
It's not. Did it happen? Like is it gonna be all right? It's did it blow up or is it fine? Like you have to just wait.
It's crazy. That's too far.
That
like
is way too
start
far.
on the moon. If we can get it working on the moon, then you can move on from there.
If we can get to the moon, I wouldn't even say move on there. I would say get to the moon, put a whole bunch of stuff on the moon.
Yeah.
Make it a relay so you can make stuff halfway to Mars.
Right.
Because it's a pretty big jump from there.
Right.
And then make small increments. Like okay, cool. We put a space station like half an astronomical unit past the moon or whatever.
And blasting off from the moon's a lot easier.
Oh yeah, a lot easier. There's so many things you don't have to deal with now. You don't have a lot of atmosphere to deal with.
Right.
So it's
it doesn't even, it spins along with Earth. So you're kind of like,
Yeah, you're tightly locked.
Yeah.
Too. And so you could.
That helps.
Yeah.
Probably,
And then on top of that, like you don't have to worry about anything stupid happening. Like, it turns out there was like rain this day, so we couldn't launch.
Right.
It's like, no, like you can, so many. Anyways, sorry, I have complete faith in the boys in the labs. I think everyone's space agencies, I hope them the best, exclusively the best. Like people don't realize how much theoretical quantum and astrophysics have like helped mankind go forward in every, like I'm pretty sure the deodorant you should be using right now is based on some chemical bond that someone discovered while doing something else.
Yeah, right, exactly.
But at the same time, like, wish all of humanity to go forward, but don't make it stupid, not for clout. Don't just throw your rocket car that you didn't release into space and then be like, okay, guys, well, that roadster? That roadster, Patrick? We shaved off another second.
So we don't have time for this. This should be in the episode. We should just start the episode. Okay, real quick, just because Adam brought it up. The Tesla Roadster had a 0 to 60 in 1.9 seconds. That is minus the 6 feet of rollout. So it's actually more like 2.1 seconds from 0 to 60. But anyway, it hasn't come out, obviously. It's supposed to come out in 2020. It has not come out yet in 2022. And but then Elon recently announced that actually, when it does come out, it's gonna have a 0 to 60 of not 1.9 seconds. But 1.1 seconds.
That's right, boys. We shaved off 0.8.
0.8 seconds from a 0 to 60 time. From like, that is like almost 50%. It's like 40% of the 0 to 60 time that he's claiming.
It was already the fastest car to ever be produced. Well,
other than the Rimac Nevera. Rimac Nevera is actually the fastest.
Well, not even. It hasn't hit production like ever. Like no one's driven it. Like
they did do a side-by-side comparison of the Model S.
And the Roadster?
Yeah, and the Roadster didn't exist, but they did do a side-by-side of the Ludicrous plus, whatever it's called, and then the Rimac Nevera. So Remington Vera has been on the road, and it did beat the claimed times of the Roadster, but that's nonsense. We can get into that in the episode though, because we're out of time here. This is, I don't know to make this a podcast episode or just 2 off the airs, but it was very
Oh man,
long.
yeah, that was pretty good.
So let's start the episode. That's it for today's episode. I hope you guys enjoyed it. Go back and watch episode 1 if you haven't already, and there should be a link to that in the annotations, as well as some recommendation videos for other games we've done. Love having you here, and hope to see you guys around.
Y'all come back now, you hear?
That was good.